So I'm talking about work I did with some students at Harvard, Dan Kapek, Prahar Mitra, and Anna Reclario. Prahar is on the job market this year. And there's also, just in the last week, been a second paper appeared with similar results by Chung, De La Fuente, and Sundram. So the starting point is going to be ordinary four-dimensional Minkowski space. And let me draw a picture of it here. The Penrose diagram for Minkowski space. And here we have future null infinity. Here we have past null infinity. And then at any value of retarded time, we have a sphere, which I'm going to label by coordinates z and z bar, and we'll have some retarded time u here. Now, ordinarily, when we talk about scattering in Minkowski space, whether it's quantum field theory or gravity and asymptotically Minkowski space, we work in a momentum space basis, and we have some plane waves coming in and some plane waves going out, and the problem is to compute, usually in momentum space, the S matrix, which tells us what incoming states travel to what outgoing states. But there's a different way of looking at it. It's really, this isn't a deep statement, it's just a kind of a tautology that we could think about it in a different way. We could think of everything in terms of this sphere at infinity. There's one at future infinity and one at past infinity. And we could label incoming particle states by x's on the sphere, which determine the angle at which they come in. In this talk, I'm only going to talk about massless states, though I believe that the ideas will extend to massive states. And also outgoing states we could label by little circles like this, and then we could label the points z1, z2, z3, and then we have some outgoing states, zn, zn plus 1, and so on. And then to each one of these points, we would attach various quantum numbers, which would include, for example, the energy, and we would know whether the state was incoming or outgoing, depending on whether the energy was negative or positive, in a convention where outgoing states have negative energy. Now, in this picture, the Lorentz group acts like SL2C on the sphere. In other words, its z goes to alpha z plus beta over gamma z plus delta. And that is the global conformal group on the sphere. And everybody in this room, I think, once they see the global conformal group acting on the sphere, they think, well, wait, why isn't there also the local conformal group? Indeed, we know that in a wide variety of critical systems that there's theorems, Zamolodchikov, Polchinski, that once you get a global group, you're forced to get the local group. So where is the local group here? Why don't we also have the local group? And the answer in this talk, what I'm going to describe in this talk, is that in fact, when you go to quantum gravity, you also have the local conformal group. And this statement has been made in different ways over the last several years, but the way I'm going to make it in this talk is I'm going to construct an operator whose insertions obey exactly the Ward identity of a stress tensor in a two-dimensional conformal field theory. That's why it's called two-dimensional stress tensor for four-dimensional gravity. In other words, I'm going to construct an operator that generates two-dimensional conformal transformations on this sphere. Now, let me just mention a side point here, is once you think about scattering in this picture as a kind of correlation function on the sphere, plane waves are not very natural. Plane waves are not representations of the Lorentz group. They're eigenstates of the translation group. And in conformal field theory, we like to work with highest weight representations of SL2C, or if that's enhanced to Virasoro, highest weight representations of the Virasoro algebra. So a very simple, seemingly simple question about quantum field theory, just massless scalar field theory or Yang-Mills theory, or is how do we write scattering amplitudes in terms of highest weight representations of SL2C instead of in terms of momentum eigenstates? Sounds like a trivial question, but I've got one of your top postdocs here, Shu Hong, working with me on it, one of my students, Sabrina, and it turns out to be a thorny question that we haven't gotten to the end of yet, but surely it has an answer. And I can talk to people more about that later, but I can't. All right, let me start by mentioning, are there buttons or do I have to jump? Whoa. Great. All right. They built this building before they had electric blackboards. Okay, so let me mention, just at the beginning, some limitations of what I'm going to say. I'm not going to consider the massive case, though I believe, based on other similar problems, that the generalization to the massive case is straightforward. I'm going to be talking about soft insertions. This operator TZZ is going to be constructed from a soft graviton. And I am not going to do multiple soft insertions. There are a lot of interesting issues that come in. The multiple soft limits may not commute, so I'm going to assume that I always have one soft operator, and all of the rest of these are at some arbitrarily small but non-zero momentum. And there's a loop correction at one loop whose effects we're trying to understand now, but we're not to the end of it. And finally, the most important point I want to make is that we're going to find that four-dimensional quantum gravity transforms up to these issues under the same group that two-dimensional conformal field theory transforms under. And you might think that we know so much about two-dimensional conformal field theory, doesn't this mean we've kind of solved four-dimensional quantum gravity? And I think the answer is no, because the kinds of representations that we're going to be encountering, we don't really know what the representations are, but it's pretty clear that they aren't the familiar ones in the conformal field theory textbooks, but nevertheless they should be some other kind of interesting representations. All right, so let me get started. So we have an endpoint scattering amplitude in quantum field theory, which we denote as out S in. And then I want to talk about an n+1 point scattering amplitude. Now I'm in quantum gravity, so that one of the particles is a graviton, which is a function of the graviton momentum q and minus, which is the same outstate but I've added graviton with negative helicity and momentum q to the out state. I could also talk about plus helicity, but I don't want to write everything twice. So now there's a theorem that as q goes to 0, a plus 1 of q minus is equal to S0 minus plus S1 minus plus order q and higher, acting on the endpoint amplitude. In other words, as the graviton, the scattering amplitude with an external graviton, as the energy gets very weak, it can be written as terms of some operators and derivatives on the endpoint amplitude. And what are these guys? Well, S0 is something that Weinberg wrote down 50-some years ago. And it's the sum with k equals 1 to n, pk mu, pk nu. So you sum over all the particle momenta, contract them. So this sum goes over all the hard particles, contract them with the polarization tensor of this graviton, and divide by the momentum of the particle times the momentum of, contract with the momentum of the graviton. So this has a pole as q goes to 0. So this is the leading term for small q. Now, what Cacciazzo and I discovered a couple of years ago is that there's a subleading term. And in fact, there's a subleading term, which I'm not going to talk about today. And the subleading term takes an interesting form. It's also a sum, and I'm working in units where 8 pi g is equal to 1, Newton's constant. It's equal to, sorry, the subleading term, S1 minus, it's equal to minus the sum over all particles, epsilon minus mu nu, p mu k, q lambda, jk, and now to type the rest of the indices, lambda nu, where this is now the angular momentum, orbital plus helicity of the kth particle, again divided by pk dot q. And so here we're replacing the momentum in the soft graviton in the leading term with the graviton momentum contracted with the angular momentum of the kth particle. And if you want to check that these formulas are gauge invariant, the leading term is gauge invariant because the sum of the external momenta add up to 0, in other words, because of momentum conservation. The subleading term, and it's subleading in q because I've got a q in the top and the bottom, the subleading term in fact, is also gauge invariant, and it relies on angular momentum conservation. And a version of this formula was actually written down using, I think, S-matrix theory by Gross and Jacqui for scalar fields in the 60s. And, okay, so that is the subleading soft graviton formula. Okay, now I want to write that in a different form, and it turns out to be secretly related to the Virasoro symmetry acting on here, and we can use this. So this formula is going to be our main tool in constructing an operator that that generates the local conformal transformations on the sphere. So the next thing I'm going to do is I'm going to introduce, let me write down coordinates in a neighborhood of future null infinity. So I have retarded time 2, u, and a minus 2 du dr, and then plus r squared times 2 times gamma z z bar dz dz bar, where gamma z z bar is equal to 2 over 1 plus zz bar squared. This is just the unit metric on the sphere. So this is the metric on asymptotically flat space. This is the metric on Minkowski space exactly. In a moment, I'm going to put in subleading corrections. So when we have gravitons, we'll have a term that looks like r czz dz squared plus cz bar z bar dz bar squared. And of course, there'll be many, many subleading terms. But at this point, I only care about these leading terms. So now I'm going to do the following. Here, I just need to do a kind of mindless but sort of difficult. Here I've got this soft theorem, which was derived using Feynman diagram techniques in terms of plane waves. And I need to write it. I want to understand what it's telling me about how things act on the sphere. So I want to use this kind of coordinate system, not the standard Cartesian coordinate system. And so what I do is you take something, for example, I write q mu. I write as omega 1. I can describe, given a null 4 vector, like the vector like that associated with the graviton, q, that's 3 numbers. One is omega, and the other number, 2 numbers, can be taken to be the 2 points, the point labeled by z and its complex conjugate on the sphere at infinity. And so it's a little bit tedious to do the transformation from these coordinates to the Cartesian coordinates. But if you do this, you find that q mu is just omega z plus z bar over 1 plus zz bar. So this would be q0, q1, q2, q3 in standard Cartesian coordinates, minus I z minus z bar over 1 plus zk z bar k. And then I have also 1 plus zz bar, 1 minus zz bar over 1 plus zz bar. Okay, so this is an alternate way of parameterizing the momentum of the graviton. That's all I've done. Now, if I want to rewrite this formula, I also have to reparameterize the momenta of the, for now, massless particles pk. I have to introduce omega k's and zk's. Even a little more complicated, I have to reparameterize all the polarization vectors. But it's all doable. It's just a tedious change of basis. And when I do that, I find that S1 minus can be written as the sum, there's still a sum over the particles k. And then I have z minus zk squared over z minus z bar k. And then I have something which I'm going to call hk, 2hk over z minus zk minus dzk, covariant with respect to zk. So S1 is an operator, right? Angular momentum is p d by dp. So this is going to be an operator. It's going to move around the external momenta. The leading soft factor is just a number, but the subleading soft factor is an operator which relates amplitudes to ones with nearby momenta. So what is hk? Well, hk is equal to a half sk. It's the helicity of the kth particle, minus omega k d by dzk, minus omega k d by d omega k. And then if I had written down the soft factor for a positive helicity graviton, I would have gotten an h bar k, which would have been 1/2 minus sk minus omega k d by d omega k. So what are these things? Well, if I take hk minus h bar k, this term cancels, and I just get the spin. So hk, if I have a particle that's coming out at some point zk, this hk is telling me how much angular momentum it's pushing through that point. In other words, it's the eigenvalue of the rotation about the point where the kth particle is coming out. Now, what about their sum? Well, the spin cancels in their sum, and I just get omega k d by d omega k. Now, if I Fourier transform that back to momentum, to position space, omega d by d omega is u d by du, because u is time. So that's u by d by du. So the sum of the two hk's is generating the dilations about the point of the kth particle. So those are the two, in other words, these are the eigenvalues of the two generators of SL2C, which leave this point invariant. Now, it's very interesting, but in this construction, yes?
Those are not dilations in this two-dimensional space, but dilations of the null coordinate? Because they affect the overall size of the momentum, but not its direction?
Okay, so if the particle is right there, is right on the null cone of the origin for the particular Lorentz group that we're talking about, it's it's the u d by du. So there are many Lorentz generators inside the Poincare group. Okay, so now, by the way, I want to mention here that there's something, this is very similar to something that people talk about in SCET, where they have some infinite dimensional symmetry called RPI, reparameterization invariance, where they have a bunch of jets which are going out to null infinity, effectively, and they change the renormalization group scale separately along each jet. And that is a lot like what we're doing here, though I haven't succeeded in making a precise connection with that work. Okay, so this is just a transcription now. And now I want to talk I want to rewrite this soft formula in this language. And it's traditional to talk, now I want to talk about gravitons. And it's traditional to define something called the Bondi news, which is the time derivative of the subleading term in the metric that is the transversely polarized gravitons. So it's no longer exactly flat because we have some gravitons going out to infinity. And what do we do next? Well, in this usual momentum space formula, we had some h mu nu, which was a fluctuation about flat space, and we had some sum over polarizations, and then you do some standard decomposition over 2 pi cubed to omega, and then you have some polarization vectors, epsilon alpha mu nu, a alpha out, e to the I, q dot x, plus epsilon alpha mu nu, a alpha out dagger, e to the minus iq dot x. So standard mode expansion. So now what we need to do is we need to rewrite, so these are the standard mode expansions for a spin 2 field. And what we need to do is to rewrite that. We need to write this field here at null infinity in terms of these standard plane wave creation and annihilation operators. And that can also be done. And what one finds is a formula that n z bar of u z bar. So this is a field that measures the strength of the graviton at null infinity, is equal to minus 1 over 4 pi squared epsilon z bar. That's the polarization factor in these new coordinates. And then some integral from 0 to infinity d omega. Omega a minus out of omega x hat plus a plus out dagger of omega x hat, and this is e to the minus I omega u, and this is e to the plus I omega u. So what is this formula saying? Well, it's just saying that if we want to write this guy as a field operator in a plane wave basis, we need to use the plane waves that are headed toward the point labeled by z and z bar. Okay, so now we've done everything we can, and we can just plug into this. And there's one more thing I wanted to find, which is n1 z bar, which is the integral du times u of n z bar. And it's equal to 1/4 epsilon z bar times the limit as omega goes to 0 of a out minus omega x hat minus a plus out of omega x hat dagger. Now, this is a particular combination because of this minus sign in here. this particular combination, so this is a soft graviton operator, which I've written covariantly as some integral over scribe plus. And this is a particular combination in which the pole cancels because of the minus sign. And so this will only pick up the subleading term. And I can therefore rewrite the soft theorem so I only have two more things to do. I'm going to rewrite the soft theorem in terms of this operator N1. And then I'm going to find a particular convolution of N1 that bears the ward identities of a stress tensor, of a 2D stress tensor. So what that theorem says is that out N1 z bar S in is equal to 1 over 2 pi 1 plus zz bar squared, the sum of z minus zk squared over z bar minus z bar k to hk over z minus zk minus d dzk, all acting on out S in. Okay, now just one more step. I'm going to define tzz as equal to integral d squared w, so I'm integrating over the sphere, I over z minus w, dw squared, dw bar of n1 w bar w bar. So this is my definition of tzz. And now, if I put that in, I find that tzz, and now let me describe the S matrix rather than describing it as out S in. Think of it as in terms of a bunch of these operator insertions. tzz of O1 On is equal to sum over from k equals 1 to n of hk over z minus zk squared plus 1 over z minus zk d dzk on O1 to On, which is the standard ward identity for a two-dimensional stress tensor in a two-dimensional conformal field theory. Moreover, I can now, for example, define a, I can take a holomorphic function, I can take a contour C, take some holomorphic function, z to the n, inside the contour C, and I can construct the integral over C tzz of the holomorphic function epsilon of z. And it then follows by contracting the contour, that will generate the holomorphic transformation epsilon everywhere inside. This is standard conformal field theory construction, everywhere inside the contour. So there's four-dimensional gravity in this sense contains, quantum gravity contains a generator of the two-dimensional Versaro transformation. Now, one peculiar thing, so I'm basically done, one peculiar thing about this construction is the fact that I constructed TZZ out of an operator I integrated over the sphere. So it looks like it could be non-local. Nevertheless, I've proven that it is local, that the ward identity is local. Now, what does it mean that, that we had to do it in this way? The answer is, I don't know, but let me throw out several possibilities. It often happens, first of all, what's local in one gauge in gravity may be non-local in another gauge. We're typically working in Bondi gauge. So it could be that there's some other gauge in which this expression becomes local. The other thing that happens is that subleading terms in the 1 over R expansion are non-locally, there's non-local relations between the successive terms in the 1 over R expansions. And it's natural to think that there are some similarities. There's a lot of similarities with anti-de Sitter space here. And those I haven't had time to explain them, but those similarities become very transparent when you write Minkowski space in a hyperbolic slicing. And from that point of view, you would expect the stress tensor to evolve something which is 2 orders further down in the 1 over R expansion than the Bondi news. And it's possible that there's some local expression for it in terms of some subleading term in the 1 over R expansion. And the third possibility is just that it's some indicator that there's something very different about the structure of the conformal group, the kinds of representations and so on that appear in this kind of context. So in conclusion, there's clearly some some precise connection between two-dimensional conformal symmetry and four-dimensional quantum gravity. We've been able to write down some very precise formulas characterizing it. We still don't understand what it really means, and there's a lot of interesting questions about it. So let me stop there.
Okay, I see a question over there. Then you.
What's the central charge?
Yes,
What are the conformal weights that you get?
okay, yeah, okay. So the central charge, I can't answer that question because I don't understand what to do with multiple soft insertions. And it's the question everybody wants to answer. But certainly, you know, I recently, these things are sometimes called Schwarzians. I mean, so sometimes called superrotations. And I recently discovered a paper by Penrose from 1962, before Versaro, before whatever. And he applied these superrotations, cutting out concepts. And he wrote down the formula for the Schwarzian that comes from a Versaro transformation on the sphere in 1962. So with a number in front of it. So there's some calculations that give Schwarzians. I mean, Juan has also written a paper with a Schwarzian in it, in which he's refusing to identify it as a central charge. So there's central charges appearing here, but they're Schwarzians appearing here, but we don't quite know the right way to think about it. Now, the conformal weights are, so essentially, if you take a scalar field in Minkowski space, first of all, you get a continuum, and this is one way that these things are different than others, than ordinary conformal field theories. It's pretty clear you're going to get a continuum of conformal weights. And again, Juan worked out a lot of stuff like this in his paper with Pimental. He was looking at de Sitter space, a hyperbolic slicing of de Sitter space. But you get a continuum of conformal weights. And the way to think of it is you want to look at Minkowski space like this. And then we do the hyperbolic slicing. And these guys are ADS3 and these guys are DS3. So it's the whole story is some fusion of ADS-CFT and DS-CFT, but you want to think of the parameter that labels the slice in a kind of Kaluza-Klein fashion. And since it's non-compact, you're going to have a continuum of eigenvalues.
Okay, Natia? You want?
I don't want it. Others might. So what's your vision? That there is an old-fashioned standard two-dimensional field theory there, which satisfies all the axioms of field theory, or is that too much to hope for?
Well, let's see, my vision. So I think that that would be a disappointing vision. We understand two-dimensional conformal field theory. This is a new kind of conformal field theory that clearly there are very special ones.
But you say to use the phrase field theory. Do you think this is a field theory or is this a generalization? Do you think there is a Lagrangian or something that will give you all these correlation functions?
Do I think there's a Lagrangian that gives these correlation functions? Well, there are lots of field theories without Lagrangians that give correlation functions. I don't think it's going to be a unitary. What's a field theory? It's got a stress tensor. We're not integrating over the metric. We freeze the boundary. It's got a stress tensor.
Does it satisfy locality property? Does it have singularities at the right places? There are a lot of things. If you put it on the torus, is it modular? There are all sorts of conditions that have to be satisfied. So I don't have an opinion. I'm just asking whether you think this will.
I think it's going to be something very different than the usual two-dimensional conformal field theories, and whether we want to call it field theory or not, it has a stress tensor that generates that generates.
It's conformal, but not a field theory.
Yeah, there's operators with dimensions. I don't know.
What do they act on? The operators act on some Hilbert space? Well, what is the structure?
Yeah, these are all interesting questions.
Okay, maybe one more question. Yes, Tom?
So the paper of Chung et al. Has an interesting explanation of the non-locality, which I'd like to hear your response to. So what they say is that if I think about a CFT, the Queen's functions of, say, two stress tensors would have singularities in them. And those would be interpreted in terms of scattering amplitudes. They'd be collinear singularities. But gravity doesn't have collinear singularities, unlike electrodynamics. And so they say, oh, because of that, it must be that the relation between the amplitudes and the stress tensor is non-local in such a way that the amplitudes don't have collinear singularity. So they do discuss multiple insertions in their paper.
Yeah, I'm afraid I haven't read that carefully, but the relationship between the amplitudes and the stress tensor is not non-local. This is a local relationship here. It's the standard relationship in two-dimensional conformal field theory.
I think what is non-local is the relationship between the insertion of the soft graviton
Yeah.
and the point where the stress tensor is inserted.
Right, exactly.
And one, I mean, if you think of the stress tensor as coming from varying the metric, right?
Yeah.
And in addition, you might think that varying the metric is like inserting a soft graviton, then you would be confused. So there's something that.
Right, but in the ADS-CFT analog, that varying the metric, you would be varying, on ADS-3, you would be varying the third term in the 1 over R expansion to get the stress tensor. It would be down by 3.
I mean, you would take the effective action as a function of the boundary metric, and you take the
Right.
first derivative with respect to the boundary metric. That first derivative is equal to then going to the third expansion in the classical solution.
Okay.
One would have thought that this first derivative with respect to the metric is similar to inserting a soft graviton. And this is a naive idea. I mean, obviously it doesn't work because you have to do something different. Yeah, I guess maybe okay. So it's a comment, or I mean normally the stress tensor is the response to varying the metric, right? And one might have naively thought that varying the metric is related to inserting a soft graviton. Now, these two statements that I made are inconsistent with the formula for the stress tensor, and well, these are formulas. So that's saying that probably it's incorrect to say that varying the metric is the same as inserting the soft graviton.
Well, we haven't precluded I don't know anything that is there something that precludes the possibility that it would be local in terms of the subleading terms of the metric? This isn't like the ADS formula. The ADS formula involves the third term. Right. If you you could take the ADS-3 stress tensor here, and that would be down by 3 powers of 1 over R. And this thing is only down by 1 power of 1 over R. So if we were to try to get that dictionary between ADS-3, the ADS-3 slicing suggests that this formula could be related to something subleading.
Okay. I don't see any more questions. Thank you very much.